All right, we're going to pick up where we left off, which is question G. Compare the change in nitrogen dioxide values with the change in N2O4. What do you notice about the relative magnitude of these values? Well, when we go back and look at the previous slide and we see our change, the numerical values of the change, we see that the value of the change in NO2 is 2 times the change in N2O4. Question H asks us to write the equilibrium constant expression, Kc, for the composition of dinitrogen tetroxide into nitrogen dioxide. So again, we look at our reaction, and so we write our equilibrium expression is equal to, Kc is equal to the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. So we get our value for Kc, or our expression for Kc. And using the values for the equilibrium concentrations from experiments 1 through 5, we need to calculate the value of Kc for all 5 experiments. So at this point, you need to get your calculator and confirm my math and confirm that you know how to do this. We look at experiment 1 and we can see that Kc, and again, all we're doing is plugging in the equilibrium concentrations into our expression for Kc on the left. So we see that Kc is equal to 1.4 squared divided by 9.30, and I get a value of 2.21. I look at experiment 2 and look at my equilibrium concentrations. Again, these concentrations are off of the previous slide. We plug in all these numbers, and again, we get 0.21. And we do the same thing for experiment 3 and 4 and 5. And you should definitely spend a few seconds with your calculator doing the math on all of these and confirming that in all 5 cases, at least to 2 significant figures, the answer always ends up being 0.21. Now, it's important here, the value of the equilibrium constant at any given temperature does not depend on the initial amounts of the reactants and the products. It only depends on the particular reaction that we're doing and the temperature at which we conduct it. All right, part J asks us to explain the difference between Kc and Kp. Kc is used for the molarity of liquid solutions. Kp is used when we have the concentration expressed for gases in terms of their pressures. So we're going to write equations 1514 and 1515 from page 617. This is of their book. But all these are expressions for Kp and Kc. And what we're trying to do is determine when would Kc equal Kp for a certain chemical reaction. All right, Kp is equal to Kc times the product of RT from the gas law reaction raised to the power of delta N, where delta N is equal to the sum of the number of the moles of the products minus the sum of the number of moles of reactants. So if there is no difference between the two, in other words, the number of moles is equal to the number of reactants, then delta N is equal to 0, and then our reaction equation reduces down to Kp equals Kc. Now, I will tell you that you will not have to convert back and forth between Kp and Kc on the AP exam. And therefore, I will not have you do any of these calculations. That used to be the case, but it is not any longer under the new rewrite in 2014. I'm putting it out there because if you take chemistry in college, you will see this again. Question L asks us to answer the question, does the equilibrium constant, whether it be Kc or Kp, normally have any units associated with it? And the answer to that is no. There are no units for the equilibrium constant. It's just a numerical value. All right, section 15.3, understanding and working with these equilibrium constants. Now, when the value of K is very large, or K very much greater than 1, the equilibrium lies to the right, and we say that the equilibrium is product favored. When the value of K is very small, in other words, K is very, very much less than 1, the equilibrium lies to the left, and we say that the equilibrium is reactant favored. Now, the reason for this is simply algebra. When I look at my K, I'm looking at a ratio of products divided by reactants, or concentration of products divided by concentration of reactants. And when that ratio is very large, or very much greater than 1, I've essentially got all products and very little reactants left. So we say that the equilibrium lies to the right. And conversely, when that number is very, very small, I've made essentially no products, and I still have essentially all of my reactants in the reaction vessel. So my equilibrium lies to the left, and we say that it is reactant favored. So we want to fill in the table with the missing information. So here's my chemical equation. N2O4 reacts to form 2 and O2. My equilibrium constant, of course, we know that at this point, we've seen this several times. This would be my product raised to its stoichiometric coefficient divided by my reactants raised to its stoichiometric coefficient. And we know that the value is 0.21. Now we want to look at the reaction written the opposite way. All I've done is take the reaction and write it as a reversal. Now I've got 2 and O2 reacts to form N2O4. So now I can write my Kc, and it should be obvious to you that if we follow our rules for writing Kc, I'm going to get the inverse of this situation that I had in the top line. And that must mean that my Kc is also the inverse. So 1 divided by 0.21 would be about 4.76. Question D says the equilibrium constant expression K for a reaction written in one direction is the reciprocal of the expression for the reaction when I write it in the reverse direction. So again, here's another reaction. Hydrogen plus chlorine reacts to form hydrogen chloride. And the equilibrium constant for this reaction, which is shown above, is equal to 47 at 400 degrees C. So in this system, which set of chemicals is favored, and how can you tell? Well, 47 is fairly much larger than 1, so we can say that the products are favored just simply because the value of Kc is pretty significantly greater than 1. Now, question F says, what's the value of the equilibrium constant in this reaction? Well, a look at this reaction shows it's the same as the first reaction, only it's written backwards, or the reverse of this reaction. So in the first one, the products are favored, so obviously in this one, Kc will be the reciprocal of 47, which will be 0.213. And now we can say that the reactants are favored because my Kc is now less than 1.0. All right, now we want to fill in the table with the missing information. Here we've been down this road a number of times, so we're going to fill in our equilibrium expression. Now when I look in the second row, I see something a little bit odd. It's not the reverse of the reaction, but it is the reaction multiplied by 2. Everything in it, all the coefficients have been multiplied by 2. So I can write my equilibrium expression just as before because I plug in the correct stoichiometric coefficients, only instead of 2 in the numerator and 1 in the denominator, it's 4 in the numerator and 2 in the denominator. And when I plug in that number, I'm going to get 0.21 squared for my Kc value. So suppose you have an equilibrium system with a chemical equation in which the reactants are A, the products are B. Now suppose you multiply all of the coefficients in that chemical equation by some constant value X. how will the new value of the equilibrium constant, K new, be related to K original? You can see down there in the lower left, my reaction, A goes to B, which goes back to A, and then I multiply everything by X. So K new is therefore just K original raised to the power of X. And we're getting this example from our notation above with N2O4 and NO2. So we want to fill in the table with the missing information in part I. So we've seen this first reaction before. We know that H2 plus Cl2 reacts to form 2HCl, and this is an equilibrium condition because I've got the double arrows. We know that Kc is equal to 47. Now when I multiply this reaction by, or all the stoichiometric coefficients by 1/2, I find that my Kc is just 47 raised to 1/2, which would be 6.9 to two significant figures. Now here again, I've done the same thing, only now I have multiplied everything by 3. So my Kc will be 47 raised to the third power, or 1.04 times 10 to the fifth. So it's important to know the concentrations of the substances in the equilibrium mixture will be the same no matter how you write the chemical equation. But the values of Kc depends completely on how you write the reaction. This is important to know and important to be able to recognize. Question J. What happens when you add two reactions together? Sort of a Hess's law type of a problem. And we're going to fill in the table with the missing information. So kind of off to the upper right there, I've got 2NOBr reacts to form 2NO plus Br2. And then Br2 plus Cl2 reacts to form 2BrCl. So for the first reaction, Kc is 0.014. And you can see the equilibrium expression that we've created. And for the second reaction, Kc is equal to 7.2. And again, that's just, you can see the equilibrium expression. So when I write looking at this set of reactions here, 2NOBr goes to 2NO plus Br2, I'm simply writing what has already been written up there. And you should also be writing this in these blank spots, and I know that K is equal to 0.014. And again, I look at the second reaction, again, essentially copying what has already been written up there, and I get my value of Kc of 7.2. Now when I look at what happens when I add these two reactions together, if I add these two reactions together, you'll note that the bromine goes away. I'm left with 2NOBr plus chlorine gas reacts to form 2NO plus 2 bromine chloride. So I write my Kc. It's the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. And I see that, in fact, this is nothing more than the product of the first two reactions. So when I multiply 0.014 times 7.2, I get a value that's approximately equal to 0.10. So if two or more chemical reactions are added together to produce a net reaction, the value of the overall equilibrium constant for the net reaction is equal to the product of the K values from each individual reaction. All right, we're going to stop there. And we'll pick up on the next page in the next video.